Well, thank you very much for that kind invitation and for the opportunity to come here from Denmark, where I live. I'm an American, but I will have a somewhat European perspective that I think you'll see will come out at times. The title I've given this, American Energy Regimes, immediately presents you with a term you might not be familiar with, the idea of an energy regime or an organization of a society based on a particular energy form. So you'll see what I mean by that as we go along. And as a historian of technology, I want to look at the past a bit in order to see what we might learn from it about where we could be going and what the possibilities are of getting there. Again, the question you raised, Irving, can we be sustainable along the lines that we're pursuing? And just to give you a quick preview, my answer is no, we probably can't. But I'm not a pessimist, but we're going to have to make some changes in the United States to move forward. I've got some assumptions that I'll just put out here right away so you see what they are. One is that energy regimes are not deterministic. That is, that just because you have electricity introduced into a society, it doesn't mean that automatically a whole set of things will have to take place, or you could plug in any different type of energy into that. Each society is going to make some choices, and each society has some constraints of its geography and its history and what its population is like. So it is a cultural thing. It's not a technological determinism that's at work here. And I'm arguing in the talk today, as I did in the book, that consumption often drives production. Usually when you do histories of energy, you focus on how do they get the stuff out of the ground and to the consumer, and the focus is on production. And the assumption is, well, the consumers, of course, want this, and so we're just delivering it. But it's often the other way around, that the consumers want something. And then people say, well, how can we get that for them? There's a push or a pull. You have to think about which is, most of the books are about production and mine was about consumption. And then there's the notion that I think is important. It comes toward the end of the talk about technological momentum. That is, a whole technological system arises around a certain form of energy. And it has a kind of long-term trajectory, like a big ocean liner. It's moving at a certain speed and direction, has momentum, and you say, well, now we don't want to go there, we want to go over here, but you can't turn in the ocean liner very fast. It has all this momentum, but wants to keep going the same way that it was going before. So that's just as a little background. Now let's just get a few statistics up here at the beginning to look at the use of energy in the United States since 1950. And the point I really want to make with this graph is very simple, is that industry is not the problem. When we heard Dow Chemical representative speak yesterday, he talked about how they had managed to curb their energy use. This didn't surprise me because you can see as a whole, industry since roughly 1970 has curbed its energy use. It is not the source of energy growth. It has been the transportation, residential, commercial sectors, or in a word, it's been the American family. It's been the American consumer who wants more and more. More television sets, more heated water beds, you name it. You all know that there's an enormous number of gadgets in every American home. So energy use by 2008, or well, today, it hasn't changed terribly much. Total energy use, not just electricity, is distributed more or less like this. This is just, probably most of you know this, but I just thought I would put it up here, that nuclear has not become a major source, nor has renewable, at least not yet. Per capita energy consumption is also worth thinking about. We've tended to emphasize here the total amount. If you look at per capita, this is a surprising thing. You'll see that starting in about 1980, these Western countries, the United States, Germany, UK, so forth, they're basically able to stop at that point the per capita use, not the total use. Americans' population is a growing population. The United States has 150 million people in 1950. Today, it's over 300 million, so it's doubled in about 55 years. So that means that the total amount's going up, but the per capita has actually been able to stabilize, but at a high level. Whereas Germany stabilized, Japan, France, UK stabilized at a lower level. This is in contrast, of course, to China and India, as one might expect. They are using less, but they're growing per capita amounts. So here's another way of looking at it, a little more fine-tuned from 1990 to 2007. This is total energy use now. This is not per capita. And you could quickly the mathematically minded can say, the population of Germany must not be increasing. And that's true. It's staying, or the same would be true of the UK. They're not growing as a population, so they're able to stop the total energy use, not just the per capita. And you could see here that and this is an important theme in the talk, is that some countries have been able to stop their energy growth at a fairly comparatively early time compared to the United States. Here's the changes in energy use in the so-called BRIC nations, Brazil, India, China, and Russia. And you could see that the increase here is considerable. So this is a contrast, is to be expected. Two different groups of countries, the Western European countries, the United States, have reached a mature stage of industrial development where you would not expect that they would have to keep growing. There are millions of people in India who don't have electricity at all, so of course there's going to be growth in a country like India. Nevertheless, the interesting thing is if you look at this for 2007, and I know it's grown again since then, this means that actually these four countries are using as much energy total as the United States, Germany, and the UK together. So there's a certain parity, you might say an ominous parity, given the world supplies of energy. Now what I want to talk about now is, with this in the back of our minds, is how did the United States end up here? And I want to talk about this idea of energy transitions, which take place about every 40 years in more recent times. But the first one doesn't happen that quickly. The first energy transition is muscle power. The first energy regime, I should say, is muscle power, lasting from, well, you could say Native Americans are using muscle power, but the Europeans bring in more muscle. That is, they bring in oxen and horses and mules, which didn't exist in the New World until they brought them here, which gave them a power advantage in clearing land, for example. And all the way up until the 1830s, muscle power is still actually the dominant form of energy in the United States. So that's not very long ago, thinking like a historian. 1830s, pretty recent. Water power in the form of small mills was there in the colonial times. It was important, but it wasn't by any means the main source of energy. So it's really around 1800 that water power starts to become important and achieves a kind of dominance by 1840. And I'll come back to all of these in more detail in a little bit. Steam power comes in the 1830s. Now, an interesting thing that most people don't realize is that although England adopted steam engines in the 18th century, the United States basically did not. At the time of the American Revolution, there are a grand total of 2 steam engines in the United States, and they're both pumping water. There are no factories in the modern understanding of a factory. So steam power really comes later, and water power tends to get forgotten, but actually it was a more important stage than most people realize, and I'll be talking a little more about that. Then you have electric power. This is familiar enough to you, I think, and oil and gas coming a little later. And then atomic power, put in parentheses because it didn't quite achieve the transition and the takeoff that was expected for it back when it was introduced. It did in France. It was conceivable it would have happened in the United States, but for cultural reasons, it did not. And of course, we are now observing an increasing use of wind and solar and alternative energies of all types. This really began in the 1970s and then sort of tailed off a bit in the 80s and 90s and started to pick up again. So those are the transitions. We'll come back to them, but notice that after we get to the water-steam transition, there's roughly about 40 years. They don't come that fast. A little tiny bit about muscle power. If you want to say, what does muscle power look like as a landscape? It's rural. You have a little house built by physical labor, cutting down trees or into logs, that sort of thing. The very earliest settlements, of course, could not be photographed, but they have recreated the Plymouth settlement just along Cape Cod there. And as far as I can tell, it is a reasonable historical recreation. And that's the kind of space that you might create using basically muscle power and live in from one generation to the next for several hundred years. If you wanted more power, you could use a horse whim. Some of you probably have seen such things, at least in museums, but you could have a horse basically walk in a circle endlessly and either go up or down with your, in this case, the the things going into the mine or back out of the mine. You can get a lot of muscle power together and do pretty impressive things. Here's an example from the Middle West. We heard about Iowa a little while ago. This could very well have been in Iowa, the Western Plains. But water power has come in by that time. So water power begins in this form here. You'll see the little mills down in the valleys, typically not located on the coast. You have to have falling water, so it's usually 30 to 100 miles inland, away from the sea, where you get this fall from a plateau down to the water sort of seacoast level. That's where the first American industry is, and it's not steam power, it is water power. In 1840, there are less than 2,000 steam engines in the entire United States, less than 2,000. And of these 2,000, some of them are on steamboats and some of them are on trains. So we're not talking about 2,000 factory engines, more like 1,200. In contrast, there are 60,000 water mills. So the basic power in society is still coming from water, even in 1850. And manufacturing then is not on the coast, it's not in cities like New York or Boston. It is located inland where you can get the falling water. And here be a typical factory kind of representation of what a town might look like. This is Lowell, the largest factory town in Massachusetts in the 1840s. Notice that there are no smokestacks. There's no industrial pollution. And the Americans were very proud of that. They said, well, this is a democratic, better form of energy use than in Britain, where they had a lot of coal, a lot of pollution, very unhealthy. So they were aware of that at that time. The Lowell mills are designed as a whole series of canals. They're still impressively worth seeing today. If anybody here been to the Lowell mills? There's a few hands gone up. There's a national park, and it's surprising how large it is when you go in, and you can take a canal ride through the area. Of course, no longer used for manufacturing. But the canals fed the water to the factories and discharged it into the river. And here's an important point. There's only a fixed amount of water. So if you want a factory town like this, you get to a certain size and that's it. If you want more power, you go upstream or downstream. You move to a tributary to develop further. The water turbine is adopted in the 1840s. Basically, it's the same idea as a steam turbine. First patented in 1820, and it's twice as efficient. In other words, you get twice as much power than you do from a traditional water wheel, and that's the basis for American industrialization, actually, not the steam engine. And the power sources then for the large textile mills are basically these water turbines. The other aspect of water power that's important is the canals, which link the towns together, and which are used for freight, but also tourists, as you see in the picture here, or immigrants. People who go to the Middle West, for example, might take the Erie Canal out here and end up in Michigan. They were quite impressive at the time. That people were amazed at these aqueducts that would carry the canals over a river. This is in what would become Rochester. That's the same place, but in the same aqueduct, but now the city has grown up. And that's my point here, is that cities developed then along these canals and, of course, along rivers, and it redistributes the economic geography of the country. Canals then spread all through the country. Here's an example from Ohio, which, of course, enabled people in Michigan also to get from the Great Lakes down to the Ohio River or the Mississippi River Basin. Steam power then comes in shortly after the development of these systems. Steam begins, but remember, there's only 2 steam engines, and there's only 1,238. 1850, just the Merrimack River, just one river system, has 900 mills, which produce about the equivalent of 80,000 horsepower. Won't sound like a lot to today, but if people have to provide that power, that's 800,000 people. Here's the shift in New England, just to give you a sense of, here's an energy transition. We're going to go through one in the next generation. Here's how long it took then. Water power to steam power in New England, basically 40 years. But my important point here is that the water power is not declining. The amount of water power in 1900 is actually greater than it was in 1870. What's happened is that as a percentage of the power, it's gone down, but not as an absolute amount. Steam power is growing more rapidly. And that's characteristic of American energy history. When they substitute one power for another, they don't actually give up the old one. They're just adding another one and having more and more. So energy transitions in the past have been a matter of adding another layer of power. They haven't been about abandoning the old systems necessarily. Here's one of the great steam engines of the 19th century, which was used to power all the machinery at a World's Fair in 1876. I know that you just have had a very big World's Fair in China, so you know what these events mean. The United States, it was 100 years since independence. Remember, they only had 2 steam engines at the time of independence, and here they had this magnificent, very large steam engine which was silent, made almost no noise, and ran everything at the exhibit. Railways, of course, are an important part of the steam energy regime. They're built in the U.S. starting in the 1830s, and they reach areas canals can't go. And they enable New England, for example, to compete directly with New York in terms of transportation. And they help to specialize the agriculture more and more. So you can get, for example, a state like Wisconsin can specialize in dairy products because they can ship this stuff everywhere. Chicago is a perfect example of what steam means, is that all these railway lines, 16 of them, converge in Chicago. Chicago has steam engines to pump water, to pump its sewage, to run its elevators, to run its grain silos. You could not imagine Chicago. Chicago could not be the city it became without steam power. It's flat, it's marshy in Chicago. There is no water power in Chicago. Now, steam power in factories changes things. It means you can put them wherever you would like. You don't have to worry now whether there's falling water. And also it makes possible very large factories. You're not limited like with water to how much power there happens to be flowing by. So it shifts the production away from the fall line down toward the coasts, the navigable streams, the convenient locations like Chicago, and stimulates the growth, and very important, it concentrates. Steam power is a concentrating power form. And improves the economies of scale then in production. It eliminates dependence on rainfall. I want to do a little comparison of canals and railways to give you a sense. Railways are 4 times faster, and the canals freeze in the winter. So obviously you have a more tightly knit economic system with the railways. But the railway freight rates go up in the winter, and in the summer you don't want to ship by rail if your product isn't too terribly perishable. You can see it costs 3 times as much to send wheat from Chicago to New York in 1877 if you went by train. In other words, the canals don't disappear. Just like I said, the water power in the factories doesn't disappear. The other interesting contrast here is that the canals disperse. That is, you can stop a boat or a steamboat on a river or a canal boat on a canal, stop it anywhere, so that the development is very spread. With the railways, you concentrate. Of course, the trains don't stop everywhere. They stop in very discrete stations, and it focuses all the growth then in those places. The canals are open to any boat, but the railways restrict and focus access as only basically the company that builds that train line. So there is a more monopolistic, hierarchical aspect to railways in their very nature, you might say. An important study was done by a man named Robert Fogel, who showed that actually the United States could have developed with very little difference in their total results economically, at least up to the Civil War and probably later, without any railways. He argued that the railways were not, strictly speaking, necessary. I'm not sure if I agree with him, but what he was picking up on is the canal system, which we tend to forget today, and the whole water-based economy was very robust and did actually serve as the basis of American industrialization. Nevertheless, no sooner is steam really in place and really in the dominant form, and it's challenged by electrical power. Here's Edison's laboratory, which you can see reproduced not very far from here if you go to Greenfield Village. This is not exactly what you see. At Greenfield Village, it's a bit more cleaned up. It looks a little more spiffy. When Edison was inventing the electric light bulb, he wasn't worrying about the grounds too much. And within basically 25 years, you've got the city of New York lit up at night, and this happens to be the first skyscraper. A building has now been torn down, part of the creative destruction of capitalism, but it's gone. Singer Tower, all lit up at night and showing you the way the Americans start to develop an electrified city, which culminates in places like Times Square. But the Americans embraced electricity very rapidly compared to other countries. And this is in contrast to their attitude toward nuclear power later, or their attitude toward alternative energies, which has not been as embracing. But electrical power, for example, in New York City, there were 5 times as many light bulbs per person as there were in London in 1903. 5 times as many. You could say they were all in Times Square, but that's not true. But there were over 1 million in Times Square. You also get a greater concentration. I talked about the steam concentrating as opposed to the more dispersed pattern of canals. The initial effect of electrification is to further concentrate. And I suggest this here with this image of the overhead line of cars, the L, which is, in this case, in Chicago, not in Chicago, but in New York. That line's not in New York anymore, but you can pack more people into the city. You can build skyscrapers. You can build subways, department stores. The density of population, the intensity of the activity is increasing. As long as the countryside is not electrified, people don't particularly want to move there. The population is moving out of the countryside into the cities. Now, one way to get a sense, again, of the pace of change. Electric motors become available, really, decent ones, in 1890. It gives you a lot of flexibility in factories, so it's possible eventually to do anything you'd like in any part of the factory. You don't have to worry about where the power is coming from. So there's a fairly rapid shift from line shafts, those overhead things that with belts coming down, to electric drive built into machines after 1900. But here, look at how slowly it still takes place. It's, even in 1910, only 18%, and the big shift only in the teens. By 1920, half of the drive is electric. So again, you see this is a fairly long process. And by 1930, 40 years after you start, you've got pretty much the domination of electric drive in the factories. I'm bringing up this 40 years over and over again because a lot of people don't seem to understand this. Al Gore challenged the American people to convert to alternative energies in 10 years. That was one of his challenges a few years back. It's not possible. I don't believe, we heard a comment yesterday, the gentleman from Dow told us that you can't get builders to implement new technologies in 10 years, not even probably 20 years. So it takes a while. People have to have time to absorb the idea, and then they have to decide when it's economically beneficial. One of the centers of the development of the electric drive was Detroit because of the automobile industry, and the assembly line, which was invented in this factory, Highland Park, which is still standing but not in use. The Highland Park plant was built without the assembly line in mind, but it, in fact, was made very open and flexible, and they did develop the assembly line there as a part of their efforts to meet demand. Again, the demand for Model Ts was so great that there was nobody worried about losing their job. They just said, how can we make more? How can we do it faster? And the assembly line is, of course, a double-edged thing. It's very good in the sense that we produce all this stuff, but environmentally, in terms of sustainability, it may not be entirely a good thing. It tends to make us move in the direction of being a throwaway society. If you don't like it, we'll just buy another one. But the electrified landscape is also part of the story. And I just show this image here of the San Francisco World's Fair of the same year as the factory. And the leading exhibit, the most popular exhibit at this fair was the assembly line, where people could come in and watch automobiles being assembled, and if they wanted, they could buy one at the fair. So this is the energy regime of electricity. And notice the growth in generating capacity, how rapid that is. This is in decades, so that's over a period of 6 decades. In some of these decades, they're literally doubling the amount of generating capacity. There's, as if they build a whole new system in addition to the one they have already. You can see that happening between points 5 and 6. That's between 1940 and 1942 to 52, more than a doubling there of the whole system. It's an incredible amount of building, comparable, I think, to what sort of things going on in China today, but the United States was doing it, of course, at a little earlier time. And the last regime comes again, even as electrification is becoming dominant, oil and gas. And you get the development, for example, of tractors, which Ford also was a major producer of at that time. And that means you're eliminating finally horsepower. Horsepower was still important all the way up till World War I. In fact, the maximum number of horses, the largest number of horses in American history was in 1918. So the muscle power regime that I mentioned at the beginning, it doesn't just disappear because of these other things. It depends on where you're looking in society. 1918, they start to really introduce these tractors, and for every tractor that's introduced, 10 horses and mules disappear. So you're losing 10 every time, and by the 30s, the decline is quite remarkable. If you want to see this shift toward use of motor oil and gas in statistical terms, here it is. You can see over 80% of the power is either coal or water in 1920, and by 1960, it's almost reversed, not entirely. There's still, between coal and water power, something like 35%. But the other thing I should emphasize here is the amount of coal being used has not gone down. The amount of coal has gone up. This is percentages we're looking at here. So the total amount of energy being used has grown tremendously. It's grown in this period 350%. So that percentages don't tell the whole story. And this, of course, means the United States eventually starts to become an oil importing country, as you can see from these statistics here, a fairly substantial amount. And I won't go into that. That's a topic for someone else to go into in detail. The nuclear power regime is also one maybe worth talking about. There was a certain naive enthusiasm for this back in the 50s, so I reproduced this postcard from Las Vegas where you see the mushroom cloud in the background. And this was thought to be an advertising point to attract people. They could go and see a nuclear explosion, you know. You could buy an atomic cocktail. And they had a beauty contest for Miss Atomic America. But those days, of course, were very short-lived. I don't know if you can read this here on the postcard. It says, from the up and atom city of Las Vegas. Of course, they lost that enthusiasm fairly quickly, and nuclear power now is not so popular or well-regarded as it was back in the 50s or maybe even into the early 60s. Certainly 3 Mile Island did a serious disservice to anybody who was trying to sell that. And even people like Admiral Rickover, who was not exactly my idea of a countercultural figure, or, you know, but he said, he was the father of the nuclear navy, but here he said before Congress, says, I do not believe that nuclear power is worth it if it creates radiation, which of course it's going to. Then you might ask me, why do I have nuclear power ships? That's a necessary evil. I would sink them all. Current gives just I know I can't do I can't do justice to this topic in just a moment, but in America there really is a backlash against the idea of nuclear power, which seemed to be the miracle source of energy that would solve all our problems back in the 50s. And today people worry about, for example, this power plant which is out in California, and you could sort of see this relationship to the ocean. And after recent events in Japan, people are not too happy thinking about this plant, which is located near the San Andreas Fault, and there could be a tsunami someday that would hit this particular plant. So Americans are less than enthusiastic, you might say, about that. More enthusiastic about renewable energies. Here's some of them in California. And you can change the demand. So I want to emphasize this as I'm coming toward the end of this section about energy regimes. The demand doesn't have to be as high as it has been in America. These are two examples. This happens to be Canada, the first one, but it's a gas-heated building with all the buildings facing south and east. It has good insulation, and the first quarter of the winter, the heating bill was only $12.50 because it's so well insulated. There are a lot of houses built along these lines in Germany as well, where they have extremely good heat exchangers, and basically the people and the appliances and the light bulbs in the house almost do the heating. If you put in a wood stove for some kind of atmospheric effect, that's about all you need. Department of Energy has built a very kind of conservative version of an energy efficient house. It's passive solar, very carefully selected appliances with good insulation, and it cut the energy use by 50%. Now these are fairly conventional solutions, but my point is that the United States wouldn't have to change its lifestyle necessarily to cut its energy use by 50% if everybody would move into a house like one of these, or if everyone would drive the most fuel-efficient cars that are available right now, the total amount of petroleum burned would be cut roughly in half. So there is a possibility of fairly radical change in energy use without much change in lifestyle. Now, just a few comments about the system in general. What I've said is, I just want to emphasize there was that early water power development, which people tend to forget, that there was a late adoption of steam compared, say, to the UK, a very rapid electrification, very rapid adoption of the automobile. Just to give you a number on that, in 1925, there's one car for every 6 Americans. And that same year, there's one car for every 100 Germans. So that gives you a sense that there's more than half of all the cars in the world are in the United States in the 1920s and 30s. So there's very high capita use of energy, and there's rapid atomic energy development until 3 Mile Island, in which case that comes to a halt. But there's slow adoption of the solar and the wind power compared to, say, Germany or Denmark or other countries. So here are some conclusions about these energy regimes. That we move from very dispersed rural society through a period of water power where it's somewhat still dispersed, but along long stretches of canal and river there's development, to highly concentrated cities. And then, of course, with the use of automobiles, people disperse again into suburbia. And now half of all commerce, half of all the people in the country, and half of all the purchases they make take place outside the city centers. They moved out. But we may be moving back. That is, it would make sense. The logic, I'm not saying that people will do this, but the logic would be, if you want to be more efficient, to reconcentrate the population in centers. Now, someone was telling me yesterday this is already happening in Kalamazoo, Michigan. So I don't know, that Kalamazoo is a portent of the future. It could happen in Detroit, which has suffered at this point a great outmigration, but then opening up a lot of land for redevelopment. So it might be that Detroit will somehow reconcentrate in the next 30, 40 years. We'll see what happens.